Hello, and welcome to the next lecture in our foundation series on physics. Before we look at the next topic, uh, a 5-minute recap on what we covered in the earlier lecture. We were talking about the force experienced by a conductor carrying current when placed in a magnetic field. So let's do a quick recap of what we learned and look at the next topic. The last lecture was all about the force experienced by a current carrying conductor when placed in a magnetic field. Now, why does that happen? A current carrying conductor creates a magnetic field around it. It becomes a temporary electromagnet. When placed in an external magnetic field, or to put it in other words, if you bring it near another magnet, it may be a permanent magnet, then these two magnets interact and they exert a force on each other. So the force experienced by our current carrying conductor, the electromagnet, because it is a force, has both magnitude and direction. So the magnitude of the force can be calculated by the formula BIL sine theta, where B is the strength of the magnetic field in which the conductor is placed, I is the current flowing through the conductor, L is the length of the conductor, and theta is the angle between the direction of the magnetic field and the conductor. So that is the magnitude of the force. The direction is given by what is called Fleming's left-hand rule, which is illustrated here. So the crux of that was a current carrying conductor in the presence of a magnetic field, an external magnetic field, experiences a force. Based on this principle, let us look at a fascinating device which has changed our world, which is so much a part of our modern lives. And that device is based on the principle that we just discussed. Today, we are going to be talking about motors. We are surrounded by motors. Motors are devices that use electrical energy and convert them into mechanical energy. If you just pause to think about the number of devices around us that use motors, you will see that we are surrounded by them. So we will discuss the principle of, or the working principle of motors, talk about many of the applications of motors in today's class. Like I said, motor converts electrical energy into mechanical energy. And you can see a schematic diagram of a motor here. And if you think of what we discussed in the earlier video, it's got the same essential components here. We have the poles of a permanent magnet. This is the North Pole and the South Pole. And a magnetic field is created between them. And the direction of the magnetic field is in that way. And what we have placed inside the magnetic field is a current carrying conductor. And that is all there is to it. By placing a current carrying conductor in a magnetic field, a force is exerted on the conductor. And that causes it to rotate. And that, simply put, is the principle of an electric motor. Before we analyze the motor a bit more, let us see how we can create simple motors without much effort. What you should remember is that a motor essentially consists of just three parts. We have permanent magnets here, which create the external magnetic field. We have a conductor here, a copper wire, which can be converted into an electric magnet. And we have the battery here, which supplies the electrical energy. So using the battery, when we cause an electric current to flow through the wire, this is converted into a magnet. Let us see what happens when the magnetic field of this electromagnet interacts with the magnetic field of the permanent magnet. How is this possible? It essentially is the interaction between two magnets, one permanent at the bottom here and one temporary, the copper wire. And this is simply a case of electrical energy supplied by the battery being converted into mechanical energy of the rotating wire. I could say this is one of the simplest kinds of motors you can build. And those of you who are curious to try it should try and build the same thing. It costs about 100 rupees to build. The most expensive part being these neodymium magnets, which you can buy for about 50 or 60 rupees. And then there is the battery and this copper wire. So for less than 100 rupees, you can build an electric motor. Here is one more demonstration. We have a couple of batteries which supplies an electric current flowing through this coil. And this coil has been placed between two magnets. And that is our external magnetic field. So what happens when a current flows through the coil? We have built another motor, and you can see the simplicity of it. It is just a current carrying conductor placed in an external magnetic field. Now, how would we apply Fleming's left-hand rule? Another way to ask the question is, how do I determine in what direction the motor is going to turn? Well, you have the left-hand rule with the three fingers indicating the direction of the current, the direction of the magnetic field, and the direction of the force. You could apply that to determine the direction in which the motor will turn. How could I make the motor turn in the reverse direction? One way would be to change the direction of the current flow. If I simply swap these wires and have current flow in the opposite direction, the motor will turn in the reverse direction. We could also swap the magnetic poles. So there are a lot of things that you can learn from a simple model like this. But I would like to remind you of Newton's third law. There are two magnets here. There is the electromagnet, which is the coil, and there are these permanent magnets. They exert a force on each other. Never forget that. There is always an action and a reaction, equal and opposite. Why does the coil turn? Why don't the permanent magnets move? Well, that is because the permanent magnets are fixed and are not allowed to move. And this coil is free to rotate. And that is why this thing rotates, but the permanent magnets do not move. But remember, there is a force acting on the permanent magnets also. So here is yet another example of a simple motor. My final demonstration on this topic is one of my favorites. And the beauty of this demonstration is the simplicity of it. So what I'm going to have is an aluminum foil, a sheet of aluminum on which, well, we will come to how it works a little later. Just watch what happens. I describe this as the world's simplest electric car. And again, what did it take to build this? Very little. Aluminum foil, a battery. This is a high discharge battery, rechargeable battery, and two magnets on either side. Uh, it takes me 10 seconds to assemble it. And it once again is a beautiful illustration of the force exerted on a current carrying conductor by an external magnetic field. Now, the aluminum foil is an important part of the experiment because it acts as a conductor and completes the circuit. It would not work if I simply placed it on a table. It requires a conductor so that it works. The current flows through the coil and causes the rotation to happen. So this is my final demonstration of a motor, my final demonstration of a motor. The last one you could see is a simply beautiful illustration of how a current carrying conductor in the presence of an external magnetic field experiences a force. Now let us get to talk more about the motor and the many applications of motors. Now, this is a schematic illustration of a motor. You can see that there is a current carrying conductor placed inside a magnetic field, and it experiences a force which causes it to rotate. There are countless applications of motors, and I have just listed a few. And it's not possible to imagine our modern lives without motors. So a fan, an electric water pump, an electric car, electric trains, they all have motors. In fact, I will leave you with one question. Electric cars, it is easy to understand, have motors. But even petrol and diesel cars have electric motors in them. Why would they need it? If they are going to be running on petrol and diesel, why would they need electric motors in them? And a big battery. You must have seen the big battery that is inside the car. And I'm not talking about electric cars either. So that is something for you to think about. Air conditioners have motors, electric trains have motors, desktop computers have motors for two reasons. One is there is a fan which keeps the processor cool. There is also a motor which runs the disk drive. Refrigerator has a compressor which is operated by a motor. Even our cell phones, our smartphones have motors. Now that is not to keep them cool. The vibrate mode of cell phones needs a motor. So as you can see, so much of our lives depends on motors. Continuing, elevators or lifts have motors in them, escalators have motors in them. There is very little that we do, very few gadgets that we use that do not in some form or shape have motors. This is a simpler diagram of a motor so that we can understand just a little bit more about the operating principle. So let's start by drawing the direction of the magnetic field. So these are our permanent magnets. So this is our permanent. So this is the north pole and the south pole of the external magnet. And there is a magnetic field which goes from north to south. And you can see that by using these batteries, we have caused an electric current to flow through the copper coil. So let me draw the electric current with a different color. So the electric current flows in this direction and comes out. Right? So what we have essentially done is put a current carrying conductor in an external magnetic field. Let us apply Fleming's left-hand rule 2 times. Once on the part of the coil labeled AB, and then on the part of the coil labeled CD. So when you apply it on this part of the conductor, by applying Fleming's left-hand rule, the direction of the current is given by the middle finger. The direction of the magnetic field should be along the index finger, and that will tell you that the force exerted is on that segment of the coil is in the downward direction. This is the direction of the force exerted on that part of the coil. Let us look at the next part of the coil, CD, where the current is flowing in the opposite direction. It's coming back towards us. So once again, by applying Fleming's left-hand rule, you can determine that the force is in the upward direction. So what we have created is 2 forces, one upward, one downward. It is going to cause a rotational effect, or it is going to create a rotational motion of the coil, and that causes the coil to rotate. So what we've done is converted electrical energy into mechanical rotational energy of the coil. So what we've done today in this lecture is talk about electric motors, how they work, the principle by which we can understand the operation of the motor, determine the direction in which it's going to rotate using Fleming's left-hand rule. I built several simple motors for you to illustrate the concept, and we spoke about the numerous applications of motors in our lives. I hope you enjoyed this session on electric motors. See you in the next class. Thank you for watching.